Isabel Vogt from MIT, and she speaks on low-degree points on curves.
So thank you so much, and thank you to the organizers for inviting me. It's a great honor to be here. So this talk, as some other talks have been also, will take classical results in algebraic geometry and try to use them to say things about a problem that I love in number theory. So if you have any questions, please interrupt me and ask them throughout the talk. OK. So this is going to be about low-degree points. So let me set up some notation about points so that we can define the sets that we're interested in. So little k is always going to denote a number field, so a finite extension of Q. And then C is going to be a nice curve over K in the sense of the previous talk. So this is smooth, projective, and geometrically integral. And I probably don't need to tell this audience that these are all very natural things from the point of view of rational points. If we don't have one of these things, we can reduce to something smaller or to one of these cases in a natural way. So we're going to assume this. And now let's talk about points. So if I have an algebraic point, so a point whose coefficients are in the algebraic closure of K, then it's actually defined over a finite extension. In particular, it's defined over the residue field, which I will denote little k sub p. So this is the residue field of the point P. And the degree of the point P is just the degree of this residue field extension. So the degree of little k of P over little k. And now my sets of low-degree points, I'm going to denote this by C lower e. And this is just going to be all algebraic points on the curve whose residue degree is bounded above by e. So alternatively, I could describe this as the union over all finite extensions f over k of degree at most e of the f points on my curve. So these are not points defined over a single number field over k. These are over an infinite collection of number fields. And I just want to draw your attention that I really did say at most e here, not equality. OK, so because I put this at most e, these sets of points nest. So on one side, I have the rational points, which is C1, which are contained inside the quadratic points, the cubic points, etc. And these all give some sort of tame filtration of all of the algebraic points on my curve. And now the motivating question for this talk that I'm interested in are how these sets CE vary with the parameter e. And the coarsest question like this that you could ask is, at what point in this sequence do I go from finite to infinite? So that is going to be the main question of today's talk. But there are more interesting questions that you could ask. For instance, when do I add infinitely many points at a step? So there's definitely more out there, but let's take this first question first. So to make a definition for that question, precise to the answer to that question, let's make this definition. The arithmetic degree of irrationality of the curve C over the base field K, which I will denote as A ir sub K of C, is defined to be the smallest e so that this set CE is infinite. So exactly the break point in this sequence between finite sets and infinite sets. All right, so to understand this definition a little bit better, let's do an example. We'll do several examples, and I'm going to organize them in a table, which is why I can't fit it over there. OK. So also probably if you've studied rational points, you know that their behavior depends a lot on the genus of the curve. So let's study some examples as we step up the genus of the curve. So genus 0, genus 1, genus 2, and genus at least 3. It will be clear later why I've put them both together and separate. And let's record something about the geometry of the curve, and then what we can say about this arithmetic degree of irrationality of the curve. So genus 0 curves, over the complex numbers, they're all the Riemann sphere, but they might not be the Riemann sphere over the ground field. But what we do have is we always have the anti-canonical linear system, which is very ample and gives me an embedding of this curve into P2 over the ground field as a smooth plane conic. So here is my cartoon picture of a smooth plane conic. And now there are two possibilities. The first possibility is that I have a rational point on my conic. So if I have a rational point on my conic, I can use that to project to any line in P2, which is P1 over the ground field. So just stereographic projection from this point defines an isomorphism between my conic and this line, and in particular gives me infinitely many rational points on my conic. So all pretty standard. Let me just record that. So the arithmetic degree of irrationality is 1 if I have a rational point. But there's another case that I don't have a rational point. So if I don't have a rational point, then it can't possibly be that this is 1, right? Because it's finite at the first stage in my sequence. So the question is, how far do I have to go before it becomes infinite? And geometry, again, comes to the rescue here because P2 has lots of rational points. So I can take a rational point on P2, and I can again project from that point on P2 to P1. And this is now not an isomorphism. That gives me a 2-to-1 map. But still, if I take a rational point on P1, then the preimage of that point will be 2 quadratic conjugate points. So this will give me infinitely many quadratic points on the curve. So 2. So that answers the picture completely in this case. And if you get bored in the talk, maybe it's already clear. Think about what these numbers are in relation to the geometry of this curve. OK, so that gives me this case. But the reason why I started writing this table down but left a lot of space there is because it really shows you the dependence on the ground field, right? Once I had a rational point, I had lots of them. So there's always some finite extension of k that I can pass to in which I'm in this first situation. So it makes sense to also keep track of the ground field. So let's do that. So if I have any big K over little k, which is a finite extension, I can also define this arithmetic degree of irrationality over big K, which is just the smallest e, so that if I take my curve, I base change it to big K, and then I look at degree e points over that, I get something infinite. So in the conic case, if I took K to be one of these quadratic extensions where it has a point, it would become 1 over that extension. So as that illustrates, you have an inequality in this direction as you go to higher and higher finite extensions. So it can decrease, but it can't decrease forever. There's a stable value. So the stable value is going to be denoted A ear k bar of C, and this is just the smallest e, so that there exists some finite extension, big K over little k, where if I base change to that extension, take degree at most e points over that, I get something infinite. It doesn't mean over k bar. Great point. So why did I put the k bar there? It's because this depends only on the k bar isomorphism class of the curve. There is another definition of this invariant, which depends only on base changing to the algebraic closure. And by the end of my talk, I think that other definition will be clear, or you already know it. OK, so thank you. That was going to be my next point. So, right, so just to make sure this is perfectly clear, let me just draw the fields that are in play in these cases. So in this first case, we have our ground field k, and I range over all of the possible degree at most e extensions, and I look at the points of my curve defined over all of those extensions, and I ask, is that an infinite set? Here, I have, actually in both of these two cases, I take k, I first make this arbitrary degree extension big K, I don't care at all what that degree is, and then I look at degree at most e extensions over that. And the thing that distinguishes these two cases is that in this case, this k is fixed, and in this case, the k is varying. OK, so now I can continue to fill in my table. OK, so genus 1 curves, again, if they have points, they're elliptic curves, but in general, they're torsors under the Jacobian, which is an elliptic curve, so isomorphic if and only if it has a rational point. And using this idea, you can show that this arithmetic degree of irrationality in this case is not uniformly bounded as I range over genus 1 curves. And this is the only genus for which that's not true. It's either bounded by, well, it's always otherwise bounded by the absolute value of 2g minus 2. But over k bar, this sort of geometric version, well, it's 1 in this case, as we just saw, and in this case, it's also 1. You can use the theory of heights and the Mordell-Weil theorem to prove that. But the situation is starkly different when I go to these higher genus cases, and this is, of course, Faltings' famous theorem, which is that if the genus of C is at least 2, then phrased like this, the k-bar arithmetic degree of irrationality of the curve is strictly greater than 1. So unwinding, there does not exist a finite extension for which there are infinitely many rational points. But I like to phrase Faltings' theorem like this because I think that it motivates you to understand what this invariant of curves is in classes of higher genus curves. The story doesn't end at knowing that it's greater than 1. Can we say something about the actual value that it takes? So that's what this talk is going to be about. Any questions about definitions? Yeah?
It's not about that, but I thought, isn't this thing bounded by the gonality of C?
Yes, but the gonality of a genus 1 curve is not uniformly bounded. The degree of the, the extension over which it has a single point is not bounded. Then you know it's bounded by 2 over that, but yeah. Any other questions? That was a great question. Yeah?
What did you mean when you called that a tame filtration?
Oh, sorry, I didn't use the word tame in a technical sense. I just meant it gives us some way of taking this large object and getting smaller, more manageable objects out of it.
Okay, cool.
Yeah, other questions? OK, so the first thing that you might try when you try to understand how this invariant behaves for higher genus curves is what you might think of as some inductive component of its behavior. So first idea is some inductive behavior, which is to say, if I have a finite map, f, from C to x, let's say this is finite of degree e, then I can, exactly in the case of projecting, oh no, it's right here. Exactly in the case of doing stereographic projection here, I can take the preimage of rational points on x, and these lie inside the degree at most e points of the curve C. Again, it's important that I said at most e. And so we see immediately that if this set is infinite, that implies that the arithmetic degree of irrationality is at most e. And we know when this can be infinite, right? By Faltings' theorem, this implies that the genus of x is at most 1. So now we see why I left the 2 here, because in the case of genus 2 curves, we get mileage out of not just considering, for genus 0, we got mileage out of the anti-canonical linear system. Let's look at the canonical linear system here. That gives me, it's again base point free, not very ample, but it gives me a map to P1 always over the ground field, and it's degree 2. And so by exactly this thing, by Faltings' theorem, the arithmetic degree of irrationality is strictly greater than 1. By the bound I just gave you over there, it's at most 2, and so it's always 2. So this inductive idea completely told us how to deal with genus 2 curves. And in fact, for small values of E, it really seems to capture a lot of the behavior of this invariant in a very precise sense, which is a theorem for small e's. So it's a theorem of Harris and Silverman when E equals 2, and Abramovich and Harris when E equals 3, which is that if E is 2 or 3, then this invariant, at least this geometric version, is equal to E precisely when E is the smallest degree of a map from C to a curve of genus at most 1. So in other words, this sort of inductive idea plus Faltings' theorem completely characterizes this invariant when it takes small values. And the natural conjecture, when you see this, and it was a conjecture in Abramovich and Harris's paper, is that the same thing should be true for all E. And that's false. So this is false for all higher E at least 4. So some series of counterexamples were given by Debarre and Fahlaoui shortly afterwards, and they're constructive. They construct curves for every E at least 4 that give a counterexample to this theorem. So they have no maps of degree E to P1 or an elliptic curve, but they have infinitely many points of degree at most E. So perhaps this is disappointing, but from my perspective, I think this is actually a reason to study this invariant. So it captures more than just the geometry of whether this curve lives in a particular Hurwitz space in the moduli of curves. There's really something more going on, and so it merits further study. OK, let me send this up. But there is something very nice that comes out of this work of Abramovich and Harris in the case E equals 3, which are some nice bounds for this invariant in terms of other invariants of curves, namely a geometric measure of irrationality, which is the gonality of the curve. So bounds. So as was pointed out in a question earlier, and immediately comes from this inductive behavior, this invariant, the arithmetic degree of irrationality, is always at most the gonality of the curve, which I can define in an analogous way to as I defined this. It's the smallest E such that there exists a map from C to P1 over K of degree E. So P1 would be my genus 0 case of that possible implication over there. But this can't always be sharp, right? For obvious reasons, it can't be sharp because C could fail to be a degree E cover of P1, but it could be a degree E cover of a positive rank elliptic curve, right? So considering that situation, So C is a degree E cover of a positive rank elliptic curve. So it has a point. So in this case, its gonality is 2. Degree 2 cover of P1 over K. So if I compose these two maps, I get that C is a degree 2E cover of P1. And so its gonality is at most 2E. So if I assumed that E was infinite, then I could use this I could bound this in terms of the gonality from below. And even though the counterexamples of Debarre and Debarre and Fahlaoui show that this is not the only thing that can go wrong, the bounds do exist. So we do have a lower bound, which is the gonality over 2. And this comes from the work of Abramovich and Harris, but it was also later noted in a paper of Fry. And I will show you the lemma. And it's a very cute argument that gives this later in the talk. OK, so this is sort of our horizon that we're working with. Gonality over 2 and gonality, this invariant, lives somewhere inside there. So the first theorem that I want to tell you is that that's the complete range that it can live in. And subject to that range, you can sort of decouple it from the gonality. So theorem 1. This is all joint work with Geoff Smith. So, OK, so for any number field, little k, and any integers alpha and gamma greater than or equal to 1, there exists a nice curve C over k such that the arithmetic degree of irrationality of this curve is alpha, and the gonality is gamma if and only if gamma over 2 is less than or equal to alpha is less than or equal to gamma. So sort of this theorem is in the spirit of the counterexamples of Debarre and Fahlaoui in that it's constructive. We actually give families of curves where every smooth member of that family has these particular invariants. And so it really came out of these techniques that we developed to prove theorem 2, that I will tell you later, which is about positive curves on smooth surfaces. So if you use those techniques, you can sort of get as an easy corollary this existence. But pointing out work to be done, because this is constructive and we're constructing families, I'm not telling you anything about the genus of this curve. So I think it's an interesting question to understand how these invariants can behave when I fix the genus. And it's not true that for the possible gonalities achieved for a particular genus, you can get everything in the range of that minimal gonality over 2 to the maximal gonality itself. So something interesting goes on when you want to fix the genus. All right. So this is the range that we're working with. This is the landscape. And we now step back and ask about what values in this range are the most interesting. And I think there's a case to be made for the two extremes. For the smallest extreme, I think that says that the geometry of the curve is especially interesting. Right? If we just think about covers of P1 or covers of an elliptic curve, that's the case where you have a very low degree cover. So it's a very geometrically special curve. But if we think about the other extreme of this range, where it's as large as possible, that's when the arithmetic is the maximally interesting. So that means that it has the fewest points that it can possibly have as allowed by its gonality, its maps to P1. So I'm going to focus for the rest of this talk on equality in this higher part of the range, which will force the curve to have as few low degree points as possible. I should also say, basically every theorem I'm going to state today you can replace this k by the k bar. So same thing holds if you want to be stable under finite extensions. All right. So examples with equality. So the first examples of this type that actually got me into this entire project is in a beautiful paper of Debarre and Klassen. Also from the 90s when all of this stuff was sort of going on, which is when C is a smooth plane curve of degree d at least 8. So a special case of a smooth plane curve are the smooth plane conics that gave us our genus 0 curves up there, but they don't fit this d at least 8 condition. OK, so in this case, they compute all of these invariants, not in this language, but the arithmetic degree of irrationality of such a curve is always equal to the gonality of this curve, which is d minus 1 if C has a rational point, and d if C does not have a rational point. And this last part about the gonality was not, independently proved by them. This is a classical theorem. So this is a theorem of Max Noether, which holds for all d at least 2. And this should look familiar, because it's exactly the case that I did up there for genus 0. So to give, so the gonality is the lowest degree of a map to P1. There are lots of P1s staring me the face in P2. There are lines in P2. And this d minus 1, this is just projection from a point on the curve. And this d is the case where I have no points on the curve to project from. So this is projection from a point off the curve. So it's a very nice description of what this is, and it agrees with the picture for points. So I like this theorem a lot for 2 reasons. One reason is that it really nails down what these invariants are. They tell you for every single smooth curve in this family, it has these invariants. But I also like it because it gives you a nice strengthening of Faltings' theorem, Faltings' basic finiteness theorem for smooth plane curves. In particular, it says if I take any one of these curves and I range over all points of degree at most d minus 2, so not contained in a finite extension, then I always get a finite set. So this is what I mean by the most arithmetically interesting. I can put the largest number down there. OK. So when I was reading this paper, again, I think it's very beautiful. But something you're struck by is what's really special about C being a smooth plane curve. So secretly, there's the surface P2 hanging out here. And also, what is this condition of d at least 8? So the second theorem I want to tell you will sort of contextualize these 2 things and generalize this result of Debarre and Klassen. Again, joint work, Geoff Smith. So now I'm going to let S over K be any nice surface with the technical requirement. Well, I'm going to write it in the most classical surface language way first. So the irregularity of the surface, which is H1 SOS, is 0. But now unpacking this, i.e. the Albanese of the surface is trivial, or the Picard group is discrete. So examples of surfaces like this include K3 surfaces, hypersurfaces in P3, rational surfaces, large class of surfaces like this, P2 in particular. So if I'm in this case, let me first write the slogan, which is sort of what this d at least 8 thing is saying. So the slogan, is this visible? Yeah. OK, the slogan is that if I have a curve on my surface that's sufficiently positive, then these invariants always agree. So then this arithmetic degree of irrationality is always equal to the gonality. Have as few low degree points as I possibly can. But now let me make this precise. So it was sort of easy to make it precise in the case of P2 because the curve classes there are just indexed by the degree, which you can obviously compare that. You can say positive as the degree gets large enough. So let's try to imitate that strategy. And so I'm going to fix a very ample polarization with which I will measure the degree of my curves. So fix P, very ample. And I'm going to run out of space, so I'm going to move this up. OK, so to remind you what I just said, fix a very ample polarization on my surface. And now I'm going to define the exceptional set with respect to this polarization. It's just going to be all of the integral classes H inside the ample cone of S. So it's just some ample divisors on my surface S, such that H squared is strictly less than 9 H dot P. So why did I call this exceptional? If I think about my cone as being sort of the worst case, where it's just a circular cone, then this H spans some ray in this cone. So here's an example of a ray spanned by the class H. And now if I think about moving along this ray, then this left-hand side is going to grow quadratically, and the right-hand side is going to grow linearly. So at some point, this is going to stop being satisfied. So there's some small exceptional cases near the bottom of my ray, and then everything is good as I get far enough out. So having made that definition, I can now make my slogan precise in one way, which is that if I have any smooth curve C, so I'll say nice, any nice curve C that embeds in my surface over K such that the class of my curve is ample on my surface, but doesn't lie in this exceptional set with respect to any choice of very ample polarization, then the arithmetic degree of irrationality is equal to the gonality of the curve. And again, same thing can be true if I put bars here. So this is stable under extensions. I'm not doing anything tricky with being over a particular ground field. OK, that was part A. But this might be slightly unsatisfying in that as I go farther towards the boundary of my ample cone, I might have to go farther and farther out on any one of these rays, because it could be I'm approaching some ray on the boundary where the square is 0, so some Neff class with square 0, and so I might have to go out pretty far as I get close to that. So one way to restrict that from happening is to sort of say that my curve lies linearly far away from the boundaries. So I can do that by fixing some closed subcone of the ample cone.
Could you say this condition is for all P?
It's for any P. Yeah, for any choice of P. I'm just making this condition effective and any P will make this positivity effective. OK, so part B, if I also restrict to lie in some closed subcone of the ample cone, N, so for N, some closed subcone of the ample cone of S, then there are only finitely many exceptional classes inside of N, which tells us that as long as I am positive in the sense of staying both away from the boundary and away from the origin, then there are only finitely many. I mean, this away from the origin was the finitely many. Then these things always agree. So you can view this as both a statement about curves and a statement about surfaces. I'm telling you something about positivity of classes on the surface, meaning that they have nice invariance. Thanks. Therefore set. Yeah, thanks. So again, I've restricted my boundaries. There's some finite set of bad classes near the origin, but if I move out away from those finite bad classes, everything is good.
Isabel?
Yeah.
So in the case of T2, there's also, you say this whole theorem of Genus that there's a lower bound in the gonality as the class of the curve that's more and more positive. Is that true here also? Do you get some geometric lower bounds?
Yes, so there are geometric lower bounds on the gonality. Let me do some examples where I can tell you explicitly what they are, but in general you can sort of give, yeah. These techniques will give you positive lower bounds on the gonality. Okay. I should say the techniques, I will point out the technique I mean when I get to that technique. Okay, so, right, so examples. So maybe by writing this exceptional set very clearly as in terms of some intersection properties, I might have convinced you that it's computable, but everything here is very computable. And in fact, sometimes it's even possible to write down precisely when this equality fails to hold for all classes in the entire ample cone, even when this non-closed boundary condition might get in the way. So let me give you now some examples. So the first thing that you might think of to generalize this theorem of Debarre and Classen is to generalize it to other surfaces whose geometric Picard group is just Z. Those are particular cases of surfaces with discrete Picard group, if it's just Z. So let's do those cases first. So in the case that the Picard group of S over the algebraic closure is just, well, I'll do Z times a very ample class, OS of 1. So P2 fits into this category, or generic K3 surfaces. Okay, so if I'm Z times some very ample class OS of 1, then the curve classes on here are now just indexed by one integer, the multiple of 1 they are. So the curves are all going to be in the linear system OS of alpha for some alpha greater than or equal to 1. And I think we could all do the exercise of figuring out what this exceptional set is in this case. I just take, the exceptional set with respect to P equals O of 1. And in that case, you will see that this arithmetic degree of irrationality is equal to the gonality if alpha is at least 9. So this looks a lot like the case of Debarre and Classen's result, except that I have an off by 1. And that's because I'm using much more general techniques. They had to do some casework in that case. But without doing casework, you can get a 9. And so I know it's sharp up through 8 because their result is sharp. I don't know of surfaces where you definitely need this difference between 8 and 9. OK, but so far I've only given you examples for surfaces with Picard rank 1. So to prove that we can compute this for some other surfaces, let me do my favorite surface of Picard rank 2. Let's take P1 cross P1. In this case, again, I can write down all the curve classes. They're indexed by the degrees of the projections onto these two factors. So I'll call those D1 and D2. And I'm going to assume 1 is less than or equal to D1 is less than or equal to D2. And in this case, let me compute everything in sight. So we have possible choice of D1 and D2. In this case, the gonality over K is the geometric gonality. It's just realized by projection onto the P1 that gives you the lower degree, or possibly the two projections if they have the same degree. But I'll only write down the K bar arithmetic degree of irrationality. But if you know, you could translate these cases and see what happens over K too. So there are two exceptional cases. I could have an elliptic normal curve. In this case, the gonality is 2, and the arithmetic degree of irrationality is 1. So not the same, but the inequality goes in the right direction. I could also have a 3-3 curve, so a canonical curve that is bielliptic. So if you want to think about this quadric as living inside P3, then this is the intersection with a cubic, and take that cubic to be a cone over an elliptic curve. That will give you such an example. So these are 3, and these are 2. So again, not equal, but the inequality goes in the right direction. And then for all other D1 and D2, I get D1 and D1. So the moral of the story is that 2, 2, and 3, 3 are not positive enough. But once I get a tiny bit more positive, the invariants agree. OK, questions? Yeah? I haven't done an example. I mean, I think that there are many good examples out there to do. I think that's a good example. The two explicit things I've given you are P2 and P1 cross P1. These are toric. I think there should be a nice combinatorial description for toric surfaces. So yeah, bunch of explicit examples out there to do. Other questions? Yeah?
Are these, in all of these cases, have these cases where the original conjecture is correct, like there's not the counterexamples to kind you mentioned by Debarre and lots of other things?
Yes. I mean, there can't be these counterexamples because I've sort of proved for you that it is equal to the gonality, and therefore it can't possibly be.
Well, except when there's a lower degree map to lower degree.
Oh, OK, yeah. But I mean, in that case, yeah.
OK.
You know where that 2 comes from. Yeah, it comes from a map to an elliptic curve. Yeah.
And will that always be the case for the examples that you treat for positive curves and surfaces?
No. So the Debarre and Klassen examples are for, or like one class of counterexamples are for curves on non-trivial projective bundles over elliptic curves, non-trivial P1 bundles, and the fact that that surface has an Albanese that is the elliptic curve is the reason why they have a counterexample. So this sort of says that obstruction of the Albanese of the surface is sort of crucial, but it's not true that even if you have a non-trivial Albanese, these bounds you can't still understand the picture like by maps to elliptic curves or maps to P1. So somehow the non-triviality of the projective bundle was important. Other questions? Maybe when I tell you, oh man, maybe when I tell you the techniques, then you'll see where that comes from. OK, so now I'm going to talk about some ideas that go into the proof of these two theorems, which I said is about positive curves on surfaces. And I'm going to focus on the case of theorem 2. So ideas in the proof of theorem 2. But I mean, most of the part until the very end is also the idea in the proof of theorem 1. OK. So if we just want to consider dimension 1 irrational varieties, we can't consider rational points. But if we allow ourselves to go up to higher dimensional varieties that are still irrational, we're back into the title of this conference, and we can look at just rational points. So that's the first idea that everybody has when they work on this problem. So what do we need to do to prove theorem 2? We need to prove this lower bound, that the arithmetic degree of irrationality is at least the gonality of the curve. Right? Because we also know the upper bound, so if we want to get equality, we have to prove the lower bound. So that means that for all E strictly less than the gonality of the curve, it has to be that this set E is CE is finite. That's just the definition. So equivalently, for all E strictly less than the gonality of the curve, it must be that sim E, which I will write as C upper E of K, is finite. So this is the idea about working with rational points on irrational varieties of higher dimension. And now we can use, we can put on our algebraic geometer hats and think, what is sim E of a curve? It's a parameter space for effective divisors of degree E on the curve. And if you're given an effective divisor, you can always take its linear equivalence class. So that's this Abel-Jacobi map from sim E of the curve to pic E of the curve, which sends a divisor D to just the linear equivalence class. And this is a good thing to do because pic E of the curve is now a torsor for the Jacobian of the curve, so things are maybe looking up. And also a nice thing about this is that we understand what the fibers of this map are, right? They're just the complete linear system of this line bundle O of D. So in particular, under my assumption that E is strictly less than the gonality of the curve, the fibers have to be just single points, right? Because, I mean, they have to be empty or a single point, because if I have more than one point, I have a non-trivial linear system, and that contradicts my gonality assumption. So this is also equivalent. Well, let me set up one piece of notation. I'm going to denote, for Brill-Noether theory reasons, WE of C to be the image of this map from sim E to pic E. And then, so this is equivalent to WE of C of K is finite. And now WE of C, as sitting inside of pic E, is a subvariety of a torsor under an abelian variety, which is the one case where Lang's conjecture on the behavior of rational points is known. So Lang's conjecture, which is a theorem of Faltings, says that if I have X, a subvariety of an abelian variety A, then the K points of X are contained in a finite union of translates of abelian subvarieties of A. So B inside of X is a translate of an abelian subvariety of A. What? Sorry, yes. I mean, contained in, but this is also contained in X, so the other direction is the easy direction. The non-trivial one is the one I drew. So, right, so in particular, if all of the B's have dimension 0, there are trivially abelian varieties, and then the rational points are finite. So I can fill this in. Because I didn't put the K bar here, I'm going to lose one direction, but if you put the K bar, you'll get both directions. This is implied by the non-existence of abelian subvarieties in WE of C. And now we have reduced ourselves to a geometric question, because I might as well base change to the algebraic closure or the complex numbers if I want, and I have to prove this geometric theorem about non-existence of abelian subvarieties. Okay, so what can you do if you have an abelian subvariety? And the answer that Abramovich and Harris give us is that you play this abelian subvariety, and in particular its group law, off of the moduli interpretation of WE of C as effective line bundles on the curve. So here's this lemma, Abramovich and Harris. So if I have this, so I'm sort of now going to assume for the contrary that I have a positive, sorry, and I never wrote positive dimension, but I said it, positive dimension. So if I have a positive dimensional abelian variety contained inside WE of C, and E is minimal for this property, so this doesn't embed in any smaller WE minus 1 or so on of the curve, then, all right, so on the level of these effective line bundles, I have a map from WE of C cross WE of C to W2E of C, which is just the tensor product of line bundles. But if I have effective line bundles in the image of sim E of C, then this agrees with just the sum map on those divisors. So let me fill all that in. So I have CE cross CE, C2E. These are just Abel-Jacobi maps. And this top map is a finite map. It just says how many ways do I take some 2E points and break them up into 2 sets of E points. All right, these are surjective. These are just their images. And now inside of here, I have B cross B. And now where does this go under the tensor product map? It goes onto an abelian variety, which I will call B2, that's non-canonically isomorphic to B. Were I to choose a base point inside of B, which I could assume exists because I'm trying to disprove having lots of rational points, so I can assume that I have one, then this is just the group law on the abelian, on the Jacobian, this tensor product map on line bundles. Okay, so, and now what's the statement? So because B2 sits inside W2E of C, its points parameterize line bundles, effective line bundles on the curve. So the points P inside B2 correspond to effective line bundles O of gamma P on the curve C. And the statement is that the complete linear system of this line bundle is base point free and dimension at least 1. Sorry, well, I'll say at least the dimension of B. In particular, we get that gonality bound that I told you before, because if B is dimension at least 1, and this is base point free of dimension at least the dimension of B, then I get a map to P1. Okay. So why is this true? So I have a little point O of gamma P here, and the complete linear system, as I said, is just the fiber of the map, of this Abel-Jacobi map, from sim2E of the curve to W2E of the curve. And so I need to know what this fiber dimension is, which is equivalently the fiber dimension all the way over to here, since this is a finite map. But now I look the other direction, and it's at least this fiber dimension, which is the dimension of B. And then the fact that it's base point free comes from a little bit more work, but it comes from this minimality of E. Okay, so we have now gotten to something that is maybe every algebraic geometer's favorite thing, which is just linear systems on curves that are base point free and have positive dimension. Like we are in a good place. We now have to use these linear systems. And we have a whole family of them. We have a positive dimensional family of them. So now to use the linear systems, this is where the surface is going to enter. So in the following way. So if my curve now embeds in a surface S, and I have this, again, this situation, O of gamma P, I'll just say this is base point free, dimension at least 1. So then it's generated by 2 global sections. So if I write that down, what does it mean to be generated by 2 global sections? It means I have a surjective map from 2 copies of OC onto the line bundle OC of gamma P. But the curve lives on the surface, so I can precompose with the surjection from 2 copies of OS onto OC. And taking this composition of OS to OC of gamma of P, we get a map to the push forward of this to the surface, which if you haven't seen this before might seem like the craziest thing to do. This is not a nice vector bundle. It's a coherent sheaf, but it's supported in codimension 1. But I've already started to resolve it by vector bundles. So here's the first step in the resolution by just this trivial bundle. But if I continue to resolve it, I'll call the kernel F. Turns out that F is a vector bundle. This is a vector bundle of rank 2, because 2 minus 0. And even better, this vector bundle knows all of the information of my problem. Its discrete invariants know all of the information of my problem. So its first Chern class is minus the class of the curve C. So in particular, if the curve is, say, ample, then this knows that it's ample in its first Chern class. And its second Chern class is the degree of gamma p. So if the degree of gamma p is, say, bounded by twice the gonality, which is exactly the situation that we're in, this vector bundle knows that in its second Chern class. And so if those bounds happen to tell you that the degree of gamma p is strictly less than c squared over 4, then this tells you that c1 squared minus 4c2 is strictly greater than 0, which if you studied stability of vector bundles is when you start jumping up and down, because this tells you that this vector bundle F is unstable. In particular, it has a maximally destabilizing subsheaf, which happens to be a vector bundle in the case, a line bundle in the case of a surface, but it's not necessarily a subline bundle. So there exists a unique maximal destabilizing subbundle, which is part of the harder, subsheaf, part of the harder Narasimhan filtration that came up on day 1. So I'm going to suggestively call it OS of minus dp inside of F. So this is some divisor class on the surface, and the fact that it is destabilizing, and I could measure that by the ample class of the curve itself, C, tells us that C dot dp is strictly less than c squared over 2. And the second thing, that it's maximal destabilizing, tells me that dp dot c minus dp is less than or equal to the degree of gamma p. And now a couple more things. I wrote it like this, as if it was the negative of something effective, and it is effective. In fact, it moves in a pencil. H naught of OS of dp is at least 2. And now the best thing of all is that this interesting divisor produced from this vector bundle that knew all of the information of our problem interacts with the divisor gamma c on the curve. And that interaction is in the following way. If I take this divisor dp and I restrict it to the curve, and I subtract off this class gamma p that I started with, I get something that's effective. So because this can be a lot the first time that you see these kinds of results, let me explain how it gives sort of the gonality results earlier in for smooth plane curves. Let me just say what would happen in that case. So as an example, if S is P2, and I have a plane curve of degree d, and I were to take as my divisor gamma the points of a fiber of the minimal degree map to P1, which we know in our heads have to be collinear, and so I've drawn them collinear, but this lemma will tell you that. So here are the points gamma. Let's suppose that we're projecting from a point x on C. Then if I use this gamma, I put it into this machinery, then what this point 4 will tell us, so I should say that D in this case will just be OP2 of 1. It'll just be the hyperplane class. And this last thing will say that OC of 1, the restriction to C, minus gamma is effective. And we know it's effective. What is it? It's just O of x. So this is what's telling us that the points of gamma of the minimal degree map are collinear. OK, so this is the key technical result that we use to understand these families of linear systems. Let me just explain how that goes, why this point 4 is so useful. It's because in the case that the surface has discrete Picard group, the possible dp's that it could show up as I vary over my p's in this B2 sitting inside W2e, they form a discrete set, right? Because the Picard group is discrete. So this effectivity condition is some lower bound on the global sections, and so that's a closed condition inside of the Picard group, or yeah, inside of B2. And so in fact, in this case, there is a single divisor D satisfying these conditions that works for all of these. And once I have that, I can do induction. I can use this effectivity to give a map from B2 to a different WF. And you win if F is smaller than E because you assumed that you had minimality. So this is the idea that gets you going to do the rest of the argument. So I'll stop there.
Questions or comments?
Hi, yeah, I missed a step in the ideas of the proof there. You had a bunch of equivalences. So if the WECK was finite, you want to go back to the CEK finite. And I think you said something about the fibers of the Abel-Jacobi map being one. But why was that if you go on the way back?
So, oh, sorry. So because I'm working in E strictly less than the gonality, it's only ever possible. I mean, it's just an isomorphism onto its image from the step up, from the sim E of C. Sorry, so sim EC of K is equal to WEC of K when E is strictly less than the gonality. It's just an isomorphism.
So you use a lot the gonality, which is the lowest degree of 2p1. You might also want to embed your curve into some Pn. It has some degree, the embedding, and if you have different embedding with, let's say, coprime degrees, you might intersect with the hyperplane and try to get lots of points with very low degree. You see what I mean?
Yes, but I mean,
this is a bit what you do.
If you also had points of high degree, then you could project from planes going through those points and get a low degree map to P1. So sort of the information of embedding in...
Sure, but it's about having several different embedding with, let's say, coprime degrees, and then you can play with the degrees being coprime, which this is... well, anyway.
I mean, yes, that's true, but yeah.
Yeah, I'm wondering, have you or someone else considered any, like, higher dimensional analogues of this? Like, for example, in cases where Lang's conjecture is known, like subvarieties of abelian varieties, you could define a sort of higher dimensional analog of arithmetic degree of irrationality based on, like, over what degree do rational points become Zariski dense.
Which is exactly what I'm asking, yeah. Yes, so you could hope to maybe apply this for things where the cotangent model is ample and globally generated. I think then you get an embedding in the Albanese. I haven't done this. The whole picture for like an analog of gonality in higher dimensions is subtle. There are several analogs, and it's just a much more difficult problem because you don't have the curved projective extension theorem, so it's not necessarily true that you always get a regular map. You might have to look at just maps defined somewhere, and the base locus comes in, so there's a lot more subtlety. I haven't looked at it, but I think it's interesting. Yeah.
More questions? If not, let us thank the speaker again.